In this math talk, we're going to examine a special kind of nonlinear relation called a quadratic relation. Now, in the past, you've worked with linear relations and nonlinear relations and recognized how to identify them. The nonlinear relations come in a variety of types, and we typically start with a quadratic relation as our first nonlinear relation to examine. Now, having said that, it's not just for that reason that we look at quadratic relations. They're incredibly important and very much applied in the real world. So we spend quite a bit of time on them. But before we get into the quadratic relation, I just want to recap what we discovered about linear relations so that we can compare what we find. So a linear relation is always of the form y equals ax plus b. Now, more commonly, you might call it y equals mx plus b, and that's fine. That's usually what we do. But I'm just putting in very general terms now, y equals ax plus b. Graphically, they look like this, and I've given you a couple of examples here. Y equals 1/3 x plus 4, y equals negative 11 over 6 x minus 2, y equals 2x, y equals negative 5, and as well the unique situation of a vertical line of the form x equals negative 5. Now that looks a little bit different from the y equals ax plus b, but we can talk about that in another video. I'm not too concerned about that right now. But in general, these are the characteristics you find with linear relations. They are all straight lines and they all produce a constant slope. In the case of that vertical line, that would be an undefined slope. We refer to that slope as a, or probably more commonly m in class. We typically have one y-intercept, and that's b, other than that vertical line case. I just include that so that we can cover all our bases, but anything away from a vertical line gives us a y-intercept, which we refer to as b. We always get 0 or 1 x-intercept. We refer to these relations as partial or direct variation. A direct variation has a b value of 0. A partial variation has a b value that's not equal to 0. And again, that vertical line is a special case where you don't even have a b value. And finally, we have no maximum or minimum value on this graph, no highest point or no lowest point. Now, comparing that to a quadratic relation, the standard form is y equals ax squared plus bx plus c. Now, if you look to the right, the bx plus c looks like ax plus b. It's a linear term. What we've added is an ax squared term, and that is what we refer to as a quadratic term. And that's what puts a bend in our graphs. So if we draw a few of them, y equals 2x squared minus 20x minus 55, y equals x squared minus 10x plus 25, y equals negative 1/4 x squared plus x minus 2. All of those are curved lines. They have a bend to them. And finally, all of these are actually connected to or related to what we call the parent function or the parent relation. And it looks like this, good old y equals x squared. If we were to talk about the characteristics of all of these graphs, we would say, first off, they're all in the family of parabolas. We call that curve shape a parabola. And I could spend an entire video just talking about the characteristics of parabolas and why they're so important to us. They have, instead of a constant slope, a constantly changing slope. That slope is constantly changing from negative to positive, and it includes 0 as well. We end up always with these with a y-intercept of c, the c value in the standard form of the equation. Now, I'm excluding any parabolas that are lying down on their sides or tilted, rotated in some way. That's beyond the scope of the course that we're working in. You end up with 0, 1, or 2 x-intercepts, and you can see all the cases there of 0, 1, or 2 x-intercepts. You do have either a maximum value or a minimum value on the curve, and we spend a lot of time examining the max and min values in our applications. So now what I'd like to do is have a look at that y equals x squared curve, the parent function as I referred to, or the parent relation, and look at some of the patterns that we see in it, or look at the characteristics that we see in it. And those characteristics we will use to graph other quadratic relations. So starting with a table of values for this graph, picking x values from negative 3 to positive 3, and then squaring all those values to get my y coordinates, I get the points negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, and then I go up the other side, 1, 1, 2, 4, and 3, 9. And pretty quickly, most students will recognize that there is a symmetry about this, a symmetry about the y-axis. In other words, every point on the right side of the graph has a mirror image on the left side of the graph, left and right relative to that y-axis. And the lowest point on this curve happens to land right on the y-axis. We refer to that point, that low point, as the vertex, and the y-axis as the axis of symmetry. The curve that we would draw through that would look something like this. Now, something that's very much worth noting is the pattern as we move from the vertex right or left to adjacent points. And it looks like this. If we go right 1, then we go up 1 from 0 to get to the next point, 1, 1. Then we go right 1, up 3 to get to the next point, and then right 1, up 5. And so we have the stepping pattern that we like to refer to as over 1, up 1, over 1, up 3, over 1, up 5. That's going to be very helpful for graphing later. Now, on the left, the pattern is identical other than you're stepping left. So left 1, up 1, left 1, up 3, left 1, up 5. And that's going to be useful, so remember that pattern, that over 1, up 1, over 1, up 3, over 1, up 5. Looking at a second graph and seeing how this reveals itself, we'll examine the graph of y equals 2, x minus 2 squared minus 6. So I will use a table of values, and I'm only going to use 5 points to examine this. So from x equals 0 to x equals 4. Plotting those points, I get this. And it turns out that the low point on this curve is at 2 and negative 6. Now that's not a coincidence. That in fact appears in the equation. Now you may be looking at this equation saying, wait a second, that's not the standard form that I referred to earlier. That's correct. This is what we call vertex form. In this form, you can actually pick the vertex right out of the equation. That's why it's very useful. So if we draw our curve, it looks something like this. Now, if we look at the stepping pattern from that vertex point, that 2, negative 6, we see we go over 1, up 2, over 1, up 6. Left 1, up 2, left 1, up 6. So the jumps are no longer 1, 3, and 5. They appear to be 2, 6, and I'm guessing the next one would have to be 10. Well, there's been a scaling of this parabola, a vertical stretch of this parabola by what we call a factor of 2. So we have this general statement that we can make about parabolas. In general, the equation of the quadratic relation, written in the form y equals a x subtract h all squared plus k, the vertex is just simply h comma k. And the stepping pattern that we get will be 1a, 3a, 5a, 7a. So whatever your a value, that will determine how large the vertical jumps are. So over 1 up 1a, over 1 up 3a, over 1 up 5a, over 1 up 7a. Now let's see if we could actually work backwards from a graph to figure out the equation. So it will go something like this. I'll pick 2 parabolas here, and I'm going to place some points on the yellow parabola. And these are the actual coordinates of the graph. If you have a look, you can see that the vertex is at negative 6 and negative 8. Well, I said that would give us our h and our k. And when I look at the stepping pattern, I go over 1 up 3. So that first jump, instead of being 1, is 3. That tells me that a itself must be 3. So if I were to write the equation, I'd say it's y equals 3, in brackets, x plus 6 squared minus 8. Trying it again for the blue graph, I place the points on the curve, and I recognize that the vertex is at 5 and 4, so that provides the h and the k for my equation. And the stepping pattern is right 1, down 1, so it's a negative step. When I write my equation, I write y equals negative x minus 5 squared plus 4. So now I'm going to have you try a few where you might want to pause the video, read the points off the graph, and see if you can write the equation. Starting with this curve, if I were to place a couple of points on that curve, I would read them as negative 4, negative 1, negative 5, negative 0.5, and negative 6, negative 1. The first thing that I would do would be to write down my vertex form and then identify h and k. Well, h is negative 4, k is negative 1, and my jump, I'm going left 1, up a half. So I'm only moving left 1 up a half. So that suggests to me that my a value is 1/2, my h value is negative 4, my k value is negative 1, and substituting, my equation looks like this, which can be simplified to y equals 1/2 x plus 4 squared minus 1. So we'll try another. Looking at the green curve, if I were to place the points as I read them on the curve, 5, 7, 6, 6, and 7, 3, I start with my vertex form of my equation, and I can identify the vertex as 5 and 7, providing my h and my k, and my a value, my steps are 1 and 3, but they're downwards, so it's going to be negative. And so I get y equals -1 times x subtract 5 all squared plus 7. Simplifying, I just get this expression, y equals -x subtract 5 squared plus 7. We'll try one more. The blue curve, if I place some points on it, 0, -1, 1, -3, and 2, -7, I recognize again that my vertex is 0, -1. I notice that my stepping pattern is over 1 down 2, then over 1 down 6. So I've got a doubling and it's upside down. So those steps are in the negative direction. Using my vertex form, I place in the value for a, which is -2, the value for h, which is 0, and the value for k, which is -1. Simplifying, I just get y equals -2x squared minus 1. So if we can write the equation from a parabola, from a graph parabola, we should be able to graph the parabola from the equation. So let's try that. Looking at the following parabolas, we're going to start with y equals 3x minus 6 squared minus 5. Well, I can read from that my vertex must be +6, -5, so I'll plot that point. And my stepping pattern must be right 1 up 3, right 1 up 9, due to that stretch factor, that a value of 3. So if I were to go right 1 up 3 and right 1 up 9, I'd have my points, and then I just draw the best smooth curve that I can through those. Trying a second one. Y equals 1/2 x plus 2 squared. Well, my vertex is maybe not quite as obvious in this, or maybe it is to everyone who's watching this. My h value is actually going to be -2, and my k value, I don't see anything there, so I take that as a 0. So my vertex must be at -2, 0. My stepping pattern should be right 1 up 1/2, right 1 up 3/2, or 1.5, right 1 up 2.5. So plotting those points, I go right 1 up 1/2, right 1 up 1.5, right 1 up 2.5, and I do it to the left as well. I get a smooth, continuous curve through that, and the graph is completed. One last one. Looking at y equals -x plus 5 all squared minus 3. I quickly identify my vertex as -5, -3, and my stepping pattern will be right 1 down 1, right 1 down 3. And so I do it symmetrically, and I draw my continuous curve. Now you're probably saying this looks all very, very easy when we have our quadratic relations in vertex form, and you would be correct. And I started by talking about quadratic relations in standard form. I'm sure you recognize the fact that we have to figure out some way to go from standard form to vertex form. Absolutely, and that's what we're going to do in the next couple of videos. Thanks for watching.